Hi, I'm Philipp. For those who don't know me, let's talk a bit about scaling Elasticsearch for your Java applications. So, those who don't know me, I'm working for Elastic, the company behind Elasticsearch, Kibana, Beats, Logstash, APM, lots of other tools. My official title is developer advocate, so I mostly talk about the good stuff that we do. Today's talk is mostly about avoiding the stupid stuff or the unnecessary mistakes that you could easily fall into with writing any Elasticsearch application. But I will have a Java application that we will use, something very simple to just try out some things and see how that is progressing. I assume that most of you are familiar with the Elastic Stack, where Elasticsearch is kind of the core, the data layer. And then I will use Kibana a bit to visualize. I won't use any other parts of the stack today. So you basically have your application to insert some data, and we'll do everything from there and see how that goes. Just to clear up one thing, because sometimes people are confused and say like, okay, what is the database behind Elasticsearch? No database behind Elasticsearch. There is a library called Apache Lucene, and Lucene is writing out the data to disk, but this is all there is. There is no other database or system involved. It's just Elasticsearch doing that. And before we dive into the actual tasks, I wanted to clear up four terms that I will use more or less frequently, because everybody should be familiar with those. If you get lost with those, you will probably have a hard time following. So let's make sure that everybody is on the same page here. So cluster, node, index, and chart are the four main terms. Let's use a picture to actually try to describe that better. So here we have, let's assume this is one cluster. So this is like the unit that works together on some data set and problem. And that cluster could be made up of one or more nodes. In my example, we are using 4 Elasticsearch nodes. So those are, strictly speaking, 4 Java processes. Normally, you would have a one-to-one mapping between a server or a Docker container and Elasticsearch. So those would be 4 servers or 4 containers normally. And within that one cluster and the nodes that are running that one, you then create indices. And indexes, it's a bit like a table in the relational world, but it's not a great comparison. So it's just like some data that belongs together, let's say that. And we have 2 indices in our example here, A and B. And then each index is made up of one or more primary shards. Those are the green, like the filled green squares. And then you can also have replicas. Replicas, you can have 0 or more, are a second copy of the same shard that you have. But it's normally for resiliency, and you also use those to scale up your read operations. So what we have here is we have our index A, and A is split up into A0 and A1, so 2 primary shards. And then they have replica shards. So we have a replica copy here, A1, and another one, A0 here. So for example, if that node would die and it would take down A0, then that node would promote this shard here to a primary shard, and all your data is still working, and you wouldn't lose any data, and you could just keep working. Same happens for the index B. So we have B0, 1, and 2. And then we have replicas B0 replica, B2, and B1. And those are the main concepts. So just to get the idea right, an index is kind of like the data that belongs together, and you can split it into one or more pieces. Those are the shards. Normally you use more shards to scale your write operations, to parallelize over multiple or more nodes. Obviously, if you only have a single node, more shards will not give you more performance because there is no way to parallelize that. But for example, here, you could use multiple shards to spread out your write operations over all the nodes. For read operations, you would normally use replica shards, because a read operation or any search operation in Elasticsearch could be served from either a primary or any replica shard. So the more replicas you have, the more places you could use to actually do your read operations. So that's the general idea. Before we dive into anything here, I'm not doing a benchmark. because this is not set up the right way, and this is also not rigorous enough for proper benchmark. So don't quote my numbers afterwards and say like, oh, this is the performance that Elasticsearch can do, because that's not the case and that's not the idea. We're just trying to look at some things that you could do wrong that will impact your performance very badly, and how you could improve that. And that's the general idea here. So this is not about getting the most out of this setup, but the idea really is to improve your setup. And I want to show you some things or some traps that you want to avoid and how to improve there. So how do we get some data? I'm using an injector. It's just a very simple Java program that we have written and provided, and it's perfect for this use case. So what this does is, or here is the URL where you can download it. Don't be confused by the URL. And I will publish the slides afterwards, so you can just find the link there. It's a jar, and you can basically tell the jar how many documents you want to create, and you can just say like, create 10,000 documents for me. And then we see how does the write performance, for example, change when we change some settings in our cluster. Let's take a very quick look into that application. So here in so this is very simple. We basically have some beans. So the basic concept we have is a person. And the person has a name, and we'll pick from a list of names in that names CSV list. We'll just pick random names from there. We will generate a random date of birth. We'll generate the gender. We create how many children a person has. And then we have, for example, an address, and we have some marketing information. So this is pretty typical setup that you might have in any kind of setup where you have any person and then you want to search, for example, for names of a person, or by date of birth, or whatever attribute they have, or by geolocation. So this data set gives you a lot of options to do stuff with it. Though we don't even want to go into too much detail on the specific data. It's more about just generating data. Then we have the generator. In the generator, we just have the options of what we want to generate. So for example, this is how many documents we would want to create by default. Those are all available as a command line parameter, so you can just generate different numbers. And we'll generate a couple of people to see how that develops over time. The actual person that is being generated here is just filling the person and the other beans with specific or randomly generated data. So for example, you would see that we have the number consult, minimum 30, and the range of 2000 that we could generate. I think up there somewhere we have a date of birth where we would say somewhere in here we have a date of birth where we generate when a person was born, for example. Here it is. So starting in 1940 and up to 70 years of age, basically we generate people. And this is the date of birth that we're setting for these people. So we're just generating a lot of random attributes, and those will end up in our data. And then probably the most relevant piece is the Elasticsearch injector. And this is just using the so-called high-level REST client. So we have a low-level REST client that is just mostly doing the connection to Elasticsearch. And the high-level REST client just gives you a nicer interface, and you don't have to manually manage serialization. And this can just insert the people that we have generated here and can push those in bulks of one or more people at one, or person objects at one time, into Elasticsearch. And this is how we generate those. This is pretty much standard of what you would expect. Like we have a low-level REST client builder for connecting to Elasticsearch, and then the high-level REST client to actually make the interaction nicer. If you've used Elasticsearch a long time ago, or let's say a while ago, we used to have a different client called Transport, which we have deprecated now. And you should switch to the REST client, because this is A, the way forward, and B, makes it much easier for us to kind of like set the borders of the cluster, because Java was the only client that was kind of like becoming part of the Elasticsearch cluster and not just connecting to it on the HTTP interface like anything else. And this is what we have switched out here. And by now, everybody should either already use the REST client or migrate to the REST client and move away from transport. But that's more of a side note. So this is how we can generate some people. So just to give you an idea what we do here, this is what I'm running here. So I have my injector jar that I'm running. I have added the debug flag so we can actually see a bit what is going on. I'm running this on one of our cloud instances, and I will remove that instance. So yeah, you can copy my password now and insert some data as well, but it will be gone afterwards, so that doesn't make much difference. Right now, I'm just generating one person and sending that up, just to show you what this would generate. So we can run this, and then it will hopefully start the jar. It's telling us that, okay, it's generating one person and it's inserting that and it's running through. This also shows you what that one person would, for example, look like. So what we have inserted here is Hafsa Giles, born 1955, female, and well, we generated some attributes here, and this person seems to be coming from Nantes. So this is all randomly generated. This is just one person, and we'll generate lots and lots more afterwards. And this is being pushed to Elasticsearch. And we will then, in the follow-up steps, we will see how that is performing. But just to give you an idea of what that looks like. So you can see here the time frame I've already set to the last 81 years because we started generating people from 1940. So this is the entire time frame in which we generate people. And you can see this is exactly that one document that we have inserted right now. So far so good. But this is not the performance part yet. We'll get into the performance part in a moment. This was just the general setup, how we generate that and how we can test out the performance afterwards. So these are the relevant options. You've seen those already here. Maybe it's a bit easier to read. So we can define like how many documents we want to insert. We'll talk about bulk a little later. And the rest is probably pretty obvious. Okay, we've seen that. This would be when I run this with 1,000. So then 1,000 people would be inserted for us. And this is just sample data that we have just seen. So how do you monitor how long this is actually taking? So the most trivial way to run this probably is we just slap time in front of the command, and then it would tell us how long did it take to run this command. So here, for example, if I just jump to the start and add time in front of it, it will at the end tell me how long this took. And I think because of running Vimix and Zoom, like my CPU is struggling a bit, so this will be slower right now. So for this benchmark, I said it's not a benchmark, also because my client is kind of like slower than Elasticsearch right now, probably. So this is just to give you an indication of how long something could take and how we can improve it. But this is not like in absolute numbers, this is not like very representative right now. So it took like 7 seconds to insert that document, to start the jar and everything. Now, let's take a bit of a look of what we could improve over time. So then we have stack monitoring. Stack monitoring is, if you don't just want to have time and it tells you, well, it took X seconds, you could have a bit more of an insight what that means inside the stack. And I'll just show you that live because it's a bit easier to see. And the screen share is kind of in my way. Go away. So now, okay. So this is the monitoring that Elasticsearch has built in. Basically, you click one button to enable that, and it gives you an overview of what you have in your cluster. So for example, you can see we are running the current version of the cluster. We have a 3-node cluster. So we have 2 proper nodes and 1 tiebreaker just to keep a quorum. But these 2 nodes here, these will do the work. And right now we have pretty much no data in there. So we could look at the indices, and we'll, for example, see that we have 1 index created right now with 1 single document. That was the person index. Let me still pick that And we'll look at some performance metrics as they come along. So you can see here, we just created that index and we will start indexing documents now. So here we had created, that's the indexing rate we had because we only indexed one document. So this is a bit slow. But let's change this and actually create some more data. So what I'm doing now is I'm running the same injector. I'm creating 1,000 person objects, one per request. So we will run 1,000 requests here. And when I run this, this will probably take a little while to run because it's 1,000 HTTP requests to the server and acknowledgement back and everything. So you can see here, each one of those debug messages is one person being indexed. And as you can see, even for 1,000 people, this is taking a while. So while this runs, and this will run for a bit, and at the end it will tell us the timing information anyway, we will see now that here the indexing rate is of course going up. So you can see we are reaching 20 inserts per second already. And you can also see the document count, like right now, the document count is still very low. If I run this often enough and with high enough values, we will reach something like 60,000 documents again for this index. And you can also see all these counts right now are very low and it looks very easy. So here, the index operations have been running. Hopefully it's finished now, and you can see this took now 49 seconds. And just for comparison, when I ran this without running Zoom and Vimix, it took 37 seconds. So it was quite a bit faster, but not that much faster. So inserting 1,000 documents into Elasticsearch is super slow. And why? This is probably one of the most common problems people, when coming fresh to Elasticsearch, have when they insert a lot of documents, is that they only insert one document at a time. And what you should do instead is you should use a bulk where you batch multiple documents together and do them in one request. To do that in our run here, what you want to do is the bulk, you can just change from 1 to 100, for example, and then it will use proper bulk requests. Remember the time we had 49 for almost 50 seconds for this run, and hopefully with 100 or a bulk request of 100, it should be faster. So let's run this. How does a bulk request work in general? So rather than sending just one JSON document, it's a new line delimited JSON, ND JSON for short. And you can see this is much faster. Rather than taking 49 seconds, this now took 11 seconds. So this will save you a lot of performance. How is one document structured? It's generally, the first line is always like the meta information. So one JSON line is the meta information, and the next JSON line is the actual document. Then the third line again is some meta information, and then you have the second document on the fourth line, and so forth. So we would have 200 lines in the document or that request that we send. The odd ones, so 1, 3, whatever, would always be the meta information, and the even ones, 2, 4, etc., would be the actual documents that we index. And the meta information would be insert into this index, maybe with that ID or whatever meta information you need, just where to store it. And it would also tell you what operation to run. So you could have in there also update or delete operations, for example. Just a side note, a bulk is just an optimization to make your requests faster. It's not a transaction. So if one request in that bulk of 100 fails, you would get it back into the error message, and it would tell you that something failed, but it would not roll back any other operations. So this is not like a transaction. It's just an optimization just to avoid having 1,000 requests, because we had 1,000 documents, 1,000 requests. Rather than having 1,000 requests, since we sent batches of 100, we only had 10 requests, 10 larger requests now. And you can see it cut the time into a quarter or so, how long that takes. Is 100 always the right bulk size? No, definitely not. Depending on some settings, and we'll get to those in a moment. Other bulk sizes might be better. So maybe we could try out 250. Let's see if that gets faster than 11 seconds. This always depends a bit on your documents and the cluster that you're sending. So there is no like exact rule. The one rule that you can remember is that sending one document per request is way too slow. The right bulk size depends really on your data. So this time it was a bit slower, so maybe 100 was actually the better time. When I ran this earlier with 100, I got this down to 4 seconds, and with a bulk size of, this is a copy paste error, this should be 500, it was slightly faster. But the optimal bulk size really depends on what you want to do. So it will depend on how large are your documents. If you have very small documents, probably you can batch more of them together. If you have 100 byte documents, throw in a lot. If you have 1 megabyte documents, probably not that many. Also, there is a request limit in Elasticsearch of 100 megabyte by default. So one request cannot be larger than 100 megabyte, otherwise it would be rejected. And then it depends, like how many nodes do you have to actually do the index operations in the background, and how many shards to spread those out. How large are your nodes? What is the general load on your cluster? If your cluster is already very busy, huge bulk requests are probably not going to be much faster because your cluster cannot keep up with them. If your cluster is pretty much idle, then probably larger bulks will work. But this is something you will need to figure out for your documents and for your hardware and configuration. So there is no one number that I can tell you that is optimal. The rule of thumb is though, 1 document per request will be very slow. So pick something better. Next up, refresh. This is a bit of an internal thing in Apache Lucene and Elasticsearch. When will a document be actually available? And this is quite different than in a relational database. In a relational database, once you insert a document or insert a row, it will be immediately readable. In Elasticsearch, when you index a document, you can always retrieve it back by an ID lookup immediately. But for do a full text search, it takes a little while until it becomes properly indexed and available. And that is the refresh interval. So there's a data structure called the segment that Lucene creates. And you need to create that segment, at least in memory, until these multi-document operations work on it and it can be found. And by default, that refresh interval is 1 second. So after inserting a document in Elasticsearch, it can by default take up to 1 second that document can actually be searched. 1 second is kind of a trade-off between having data quickly available and not creating too many of these segments. Because what happens in the long run, if you create a new segment every second, you will have a lot of segments afterwards you need to search. That's why what Elasticsearch does in the background is it will merge those segments over time together to create larger segments. That is, of course, a bit of a heavy operation. So what would be beneficial is if you had fewer but larger segments in the first place. And for that, you could change that refresh interval. So you could just set, rather than having the default of 1 second, you could change that refresh rate to 30 seconds. So only every 30 seconds would you create a new segment. So it might take up to 30 seconds until your document can be found, but it will make your cluster or add less load to your cluster and potentially make it A, faster to insert, but B, also you have fewer merges afterwards. So that will save you resources. Or you could even disable refresh entirely. What that would do is Elasticsearch would only do a refresh when it needs to do that internally. And that is mostly useful when you do a large bulk insert. Like imagine you need to index 1 billion documents and you're not reading them yet because you're just throwing in all the documents. You could just disable that refresh rate, insert the 1 billion documents, and then you could just call a refresh. It's basically an underscore refresh on the index explicitly. To do the operation, and that would make the bulk indexing operation much faster. So we can try that out if that will improve the setup here. To do that, probably the easiest way is in index management. You can see here we have person, And we can here manage the index, and we have the index settings. And in the index settings, it tells you what is currently being set. And somewhere in here, we have a refresh interval of 1 second, I'm pretty sure. And you could then change that. So here, when we edit the settings, we could just set this to 30 seconds, for example. Save this. Now this has been applied, and now we can add some more documents. This time, because I will pick a larger bulk, we'll just add more documents in one go to also see if that actually makes a difference. So here, let's say I will do again, I will insert 10,000 documents now, and now I will run that with, let's say, 200 bulk requests to see how long that takes. And afterwards, we can change the refresh rate again and see if that changed anything. And by the way, you will always need to test all the combinations. So once you change the bulk size and then you change the refresh rate, you will again need to check, like, is this the right combination of bulk size and refresh rate? Or will this make your operation slower? Okay, so this took 22 seconds. Let me edit this one here again. Edit index settings. We set this back to 1 second. So we've added that, and I didn't mean to start Brave now. Go away. Now we can run the same operation, and now we can see if this one will be faster than 22 seconds. So let's see. Our bytes of 200 are swinging by. Okay, looks like, what did we have before? So before we had 22 seconds, now we have 18. So this time the lower refresh rate actually was faster, which might be unexpected. I don't think for this use case or for this number of documents, we will actually see much difference because these are too few documents. But if you load 1 billion documents, you will see the difference. But you probably don't want to wait now until we have inserted 1 billion documents. So for small indices, it probably doesn't make that much sense. But for very large index operations, especially if you have bulks, it will make more sense. But it is a trade-off between how quickly are your documents searchable and the resources you need for them. Okay, so we've seen those. Load distribution is another interesting thing. First off, we need to clear up what kind of node types do we have in Elasticsearch. So the first thing is there's one node type that keeps track of the state of which indices do you have in your cluster, which nodes are in your cluster, what is the mapping or the schema of those. Those are the master nodes. Once you have a couple of nodes, it is a very good idea for the cluster stability to have dedicated master nodes. This is more of a stability than a performance thing though. So for example, our cloud offering by default, I think once you hit 6 nodes, will create dedicated master nodes automatically for you. Something like between 5 and 10 nodes, once you hit those, you want to have 3 dedicated master nodes who just keep track of the cluster state. Because if those are not working well, then your cluster will have a very bad day. Then you have the data nodes, which do the actual work. Those normally have fast disks, quite a bit of memory, probably not so much CPU, but decent amount of CPU, and they do the actual work. So they will insert the data, they will run the queries. You can optionally also have so-called coordinating nodes or coordinating only nodes. What they do is they're like a smart proxy. They are another Elasticsearch node, and they don't have any data themselves, but they know the topology of the rest of the cluster, and then know like, okay, you're searching this index, and I know it has shards here, here, and here on these nodes. And it will then go know it has to query those nodes, fetch the data, and hand you back the original result. The idea is if you have a lot of requests, especially if you have like large aggregations, it might be beneficial to not put those on the data nodes because they should just be busy serving requests and not generating those requests and managing or coordinating those. So coordinating nodes can help you to make your cluster also more scalable. Those will normally only come in handy or be required if you have really large clusters or specific setups though. Topology-wise, normally you connect to one or more Elasticsearch nodes, and then if you use any of the official clients, like the Java client, they will automatically sniff out the entire topology of the cluster. So one node will tell your client basically, hey, I know there are these other nodes, and you can talk to all of them. You could, for example, only explicitly configure the coordinating only nodes if you have those, but otherwise you could just provide one single node, and then that node would tell your client, hey, here are all these other nodes that you can query. If you use our cloud service, it's, by the way, slightly different. You just get one proxy, and the proxy will do the distribution in the background, but there is just one endpoint that you will always talk to, and that will do the work for you. Distribution-wise, how do the requests work? By default, it will be round robin. So let's assume you have a 3-node cluster, and then you do one write operation and it will go to one node. And then you do another write operation, it will go to another node. And it will just go between those nodes and try to evenly distribute those write and read operations. For read operations, there is now, since 7.0, also a new mode called adaptive replica selection. And the idea is, since you can search either on the primary or any replica shard, sometimes maybe a node is busy. And then if you do a search operation against a busy node, it will slow down your search and people will be unhappy. And what we now do automatically in the background is basically with every request, we send back some meta information about how busy the node is. And then every coordinating node will automatically, or any node in the cluster that runs any queries will keep track of that and know approximately how busy the other nodes are. And then see that, okay, you have one primary and one replica shard, and it will automatically go to the shard that is less busy. So it will know which node is less busy, that has a copy of the data, and just query the less busy data. In 6.32, I don't know, at some point it was added and you had to turn it on in the previous major version. Since 7.0, this is on by default and you can just use it and go out there. Okay, indexing and chart strategy. Previously, what we had in Elasticsearch was 5 primary shards and 1 replica, which was nice to show the use case of the data is automatically split up and distributed. The problem was there is a cost to every single shard, and lots of people had too many shards. This was the #1 performance problem, I think, that support saw and that we saw on Stack Overflow and Discuss. That's why in 7, we changed the number of primary shards to 1. So every index has 1 primary shard and 1 replica shard. And just that you have fewer shards. And then it's a question of what kind of data do you have? How do you structure your indices? So one index has by default 1 primary shard. If you have a lot of data, you might want to change it. We'll get to the shards in a moment. For the index pattern, there are generally 2 ways to structure your data, or it depends on what kind of data you have. First, you have some more or less static data set, like a full text search data set. For example, Wikipedia, the documents grow a bit, but it's not like they're doubling every week or so. So you have a more or less static use case. That's kind of like, the full text search use case that you commonly have. And then oftentimes you have a time-based data set, which might be logs or metrics or some kind of events, because there you will get new data every day and it will just keep growing and growing and growing and growing. So for the static data set, you just create the index with the right number of shards. For a time-based approach, what you want to do is you want to create some index strategy of how you want to create those indices. So for example, let's assume my personal index, for some reason, I would add 1 million new people every day. And then your shards and indices would keep growing and growing and growing. until they're humongous, and then a node might be overloaded, and B, there is also a limit of how many documents you can have in one shard, which is somewhere around the 2 to the power of 32 limit, because the count in there is only an integer. Might be changed in the future, but that's a very high limit anyway. But if you have this pattern where you have new log data, for example, every day, what you want to have is like a daily or weekly pattern. So you create a new index every day. For example, you have logs, dash, and then the date, and then you just create a new one every day. And also, if you want to remove old data, you can just drop an entire day. Because what is very expensive would be, for example, running a delete by query where you remove individual documents, where you say anything older than this date has to be removed. That is a very expensive operation in Lucene. So you don't want to do that. Even better, we now have a rollover API where you basically can define a condition, and you can say, once an index hits X gigabytes of data, for example, I want to create a new one. And that would guarantee that all your indices and charts are evenly sized, which is one of the things that you generally want to have in a cluster. Shard size, this is a very common question. Shards should be in the gigabyte range. If you have shards with some kilobytes or megabytes of data, you're not using their full potential, because there is an overhead in every single shard in terms of file handle and memory. So if you have thousands of shards on one node, which are all tiny, you're not doing yourself any favor, and your cluster will be unnecessarily slow. So a shard should potentially be larger than 10 gigabytes, depending a bit on the use case. Full text search use cases might be a bit on the lower side, like 15 gigabytes or something like that. Log use cases might be a bit bigger, like 50 or 100 gigabytes per shard. Again, you can benchmark that. Simon, our tech lead in Elasticsearch, he used to say, like, you take a single shard, you put in as much data as you can. When it explodes and doesn't work properly anymore, in terms of performance, then you know this was too much. And then you see, like, up until which point does it work? And that gives you an idea of how large your shards should be. But as a rule of thumb, greater than or bigger than 10 gigs, maybe around 50 gigs, which is also the default that we would create with the beats since 7.0. And then there's another rule that is important. Because I said there is an overhead per shard, you should not have more than, let's say, roughly 20 shards per gigabyte of heap. So, you know, if you have 30 gigabytes of heap, you should have less than 600 shards. And that's really the upper limit. Like, if you only have 50 shards, that's probably much better performance-wise. Also because if you have 50 shards of 50 gigs, that's already a decent amount of data. Or maybe you have 200 shards and each one has 50 gigs. That's actually quite a busy server potentially already if you have lots of queries. So just as a rough number, don't create tiny shards and don't create too many per node because of their overhead. We can, by the way, while we're at it, no, not Brave again. In the monitoring, go away, Brave. In the monitoring here, while you saw the indexing rate here, this was when we were running our indexing rate, you could see how many documents we were pushing. You can see the index memory of how much memory this needs. So this only has a couple of thousand documents now, but you see the index just needs, I don't know, that much memory. We have made some recent improvements in that as well. So it shouldn't be as memory hungry as it used to be. But there's still some overhead per shard in terms of memory, so don't go too wild there. And you can see how our disk size grows again when we insert documents. Okay. Pagination, this is, if you write your Java applications and you need to show these pages of like you have that many hits, is something that is also an important performance consideration. And to keep it simple, I will just show you that directly in Kibana's console. So this is just running like a curl command, but your application would run the same command. So this is the typical pagination use case. I run this query, I get like some people out of that. Let me generate some more people in the background. Yeah, let's create 10,000 more. So we have a bigger data set to actually query. So I can run this, and you can see this takes like 4 or 5 milliseconds to fetch 0 to 10 people with their date of birth ascending. So you can see here the oldest person is from the 1st of January 1940. So now I could go to the second page, so starting from 10 and then getting the next 10. And when I run that, you can see this is still around 4 or 5 milliseconds. Now, what happens if I increase that to 1000? Suddenly, it's okay, 8 or 9 milliseconds. What if I go to 5000? So this now is even slower. So this time, this got 3 times slower. Why is this query so much slower? And this, by the way, is not specific to Elasticsearch. This is a problem that any data store has, where you have this deep pagination. And that's the reason why you shouldn't do deep pagination. What this does basically is, you tell it, I want to create, or I want to get documents ordered ascending from the date of birth. And it will sort the documents. It will sort the first 5010 documents. Then it will throw the first 5000 hits away and then give you the remaining 10 documents. This is why deep pagination is so expensive, because at first you just have to, you sort a small data set and just return that. And then the deeper the pagination goes, the more data you have to sort and generate, but you only want to have this small chunk at the very end. And you throw the rest here, you just throw away because you don't want that. And that's why deep pagination is getting more and more expensive. So if I increase that to 9,000, then yeah, it's again around 20 milliseconds or so. So this is just getting more and more costly. Elasticsearch, by the way, is trying to protect you from yourself. So if you go to 10,000 and want to get the hits from 10,000 to 10,010, what Elasticsearch will do is it will actually throw back an error, because you can at most return either 10,000 documents or also sort 10,000 documents and get a subset, because otherwise your query would be very expensive. And Elasticsearch fights back against that and doesn't allow that. If you read the error message, it, by the way, says something about max result window. So we could change this setting on the index. So we could just change this to 100,000 or so. But doing that is not really recommended, because again, it's very expensive. You would just sort a huge amount of data in memory and then just throw away most of it and just return a very small subset. Or sometimes people want to return like 50,000 documents in one go. And we always ask, like, what are you doing with that? Which user is reading 50,000 documents in one go? That doesn't sound like a sensible use case. There are 2 alternatives to make or avoid deep pagination. And you don't have to change this setting, which is there for a good reason. So the first one is search after. Search after is basically, you search some page, and then it takes the last document and the sort condition and makes that the starting point for the next page. So rather than just sorting everything before, you just have a condition which excludes all the documents before, and then you can just take the documents from that starting point that you have. The one condition that you have is that this needs a total order. So if you sort by birth date, that might not be enough because it might not fully sort all the people. You would then need to have a second search criteria. But you could, for example, use the ID of a document, which would make it unique, and that would create a total order. And then you could just always say, like, okay, this was the last document. I want to get the next, I don't know, 10 documents from this point on. This is what you can very easily use in the continuous scroll. So you end up at some point in the scroll, and then you just get the next X results from there, and then the next X results from there. What search after cannot do is you cannot jump from page 1 to page 7, because it doesn't know the condition for page 7 anymore. But normally this is not so relevant. Most people want to go from page 1 to 2 to 3, etc. If you search through GitHub, which also uses Elasticsearch heavily, there are I think if you scroll through the commits, you can always only go to the next page of commits because it's exactly using search after. Because otherwise it would potentially be a very expensive operation. The other thing that you can use is scroll. Scroll is basically for machines to just fetch all the data. It creates basically like a state on the server. So it has a bit overhead in that regard. And it's kind of fixed when you create the scroll. It will not put any updates or edit documents into the scroll, but just take the documents from that point in time, and then just walk through or let you in multiple requests fetch all the documents from that scroll. But that's normally mostly useful if another system needs to fetch a large amount of data, but not for humans to get the data. That's not what it's made for. Okay. Timing-wise, I think we have like 8 minutes left or so, so we are almost there. One thing that is very handy here, by the way, if I take this query, and you can go to the search profiler here, so we can just say, this is the query that I want to run, and we'll make this actually run. And this is the index where I want to run this person. It will actually run this, tell you how long did this query now take, and you will see for every single shard involved, so we have 5 primary shards in this example because that's the way I still set this up. And this shows you for each single shard, how long did it take? And you could also see the details of where did you spend your time in here. And you would see that you're just fetching a lot of documents, like you're spending a lot of time to iterate through all the next matching document and jump from one document to the next. So this is because you're generating 1,000 documents and just take 10 then, or actually 10,010 documents is what you generate, but you throw 1,000 away. This is where you're spending your time. And this is a very nice way to debug where are you spending your time and what is slow and what you could improve in your query. You could also, by the way, from your application, just turn on query logging, like a slow query log. Log any query that takes more than 500 milliseconds, for example, and then run that through the search profiler to figure out why is your query slow, and then work on improving that. This is what you've just seen. One short mention of benchmarks. We have our own benchmarking tool called Rally. I didn't show it because it's written in Python and I didn't want to come to a Java conference with a Python. But it's basically a structured way to create nodes for a specific setup and then run a benchmark against that. And that is very helpful if you need to figure out like, oh, we need to have this data size or this many queries or these search operations, and how can I ideally configure my cluster, or how large do I need to create the cluster to actually keep up with that workload? And Rally can do that for you. We also use Rally a lot internally with nightly benchmarks. So benchmarks.elastic.co would show you how these look like. And you can see here we have multiple use cases. So this is geopoints in full text search. We have like HTTP logs. There are multiple data sets that we use. And then we run these against various setups. So with different heap sizes, with different configurations of Elasticsearch. And you could see how over time, every night, those change. Those are bare metal machines. Nobody's touching anything to avoid breaking any benchmarks. We also use those quite heavily to benchmark versions. So if I'm not mistaken, this was, I think, Elasticsearch 1.x. This was 2.x, 5, 6, and 7. Or if you would scroll further down in the Kibana dashboard, you could see at the bottom like what is which version. And you can see these are the different installation options. So for example, different licenses, this would use full disk encryption, and you would see how much performance this costs you. So we do benchmark a lot internally to just see that, or make sure that stuff keeps improving over time and not gets worse. Be very careful when somebody runs that against competitors, because then normally you end up with some benchmarking. And that's why we don't do those. Like we benchmark a lot internally, but comparing products is often not fair. Like you could just skew the benchmarks from some competitor very easily. For example, for Elasticsearch, if you don't use bulk requests and just do one request at a time, you could just make that easily 4 or 5 times slower than normal, and without changing anything else. So it's very tricky to get the benchmarks right, because most of the time you don't know other products that well. Benchmarks mostly make sense if you have your scenario and your setup and your data. Then you can benchmark how does that work on different platforms. Vendor benchmarks I would always treat very carefully though. So to wrap up, we have covered like monitoring. Like the monitoring in Kibana is very nice because it shows you like how many documents do you have? What is the latency? What is the indexing or search throughput? You could see garbage collections. You could see under how much memory pressure each node is. Use bulks, potentially change the refresh interval for large bulk inserts. We talked a bit about load distribution and how to improve that. Indexing and shard strategy. The most important point is don't overshard. Like having 1,000 shards per node or more is a bad idea. But we have seen people push 10,000 shards on a single node, and it still worked, but maybe not perfectly. Deep pagination is the devil. Don't use that. Be careful with benchmarks. Always run your own benchmarks. I think those are the most important points. And one of the main answers here is, by the way, it depends. So there are very few absolutes. It's just like trying to give you some ideas of what you could use to improve your performance and make it better over time. But most of the time, there's not one rule. This is what you must do to actually work this out. But you need to figure out what works for your data, for your hardware, for your specific queries and load. What are the right settings? For most more complex systems, there's unfortunately not one size fits all. Final note, because sometimes people ask like, okay, you've shown us a lot of cool stuff. How can I use that? Everything I've shown you is freely available and open. So you can just download that, run it yourself. I've run it against our cloud service because I'm lazy. If you want a cloud service, that's where you get all of those as well. But everything I've shown you is freely available and you can just go wild yourself as well. That's pretty much it. That was scaling Elasticsearch. I hope you have learned something, and we'll see what the questions will bring. So I will switch back to Vimix. Do we have any questions?
Dear friends, if you have any questions to Philipp after the talk, please write in the chat and I will read it to Philipp.
Perfect. I think we almost got the time perfectly, right? We have
yes,
1 minute
almost
left. Yeah.
The question from Vitaly: are there any tips and tricks for serverless Elastic usage?
So, I mean, the Elasticsearch itself is not really a serverless application. If you want to write, I think the one thing that even in serverless, you should try to not have single requests, but try to create bulks. That will probably be one of the main things where I would be careful. Other than that, I don't think that serverless, at least for the data store, really changes all that much. It's still your regular requests.
Thank you. Any other question, guys? Please don't be shy. We still have a couple of minutes. And I would like to remember that you can join the question and answer section in Zoom conference and talk to Philipp personally, ask all your questions and have more private conversation with all your questions.
I'll jump to Zoom right afterwards.
Yes, exactly. Okay, it looks like any more question, Philipp. So I would like to thank you for your talk and for joining the Java Fest online today.
Thanks for having me.
And then please join the Zoom room, and I hope you will have people to talk about.
Perfect. Thank you. I'll hop over to Zoom. See you in a minute. Bye, everyone.
Okay.